Hi everyone, good day. I am Perrie Perocho from the Department of Manufacturing, Engineering and Management, de La Salle University, Manila, Philippines. And I'm here to present our study titled Machine Learning-Based Classification of Corn Seed Viability using Electrical Impedance Spectroscopy. So for the background of this study, corn is an essential multi-purpose crop that supports human life and economic growth, with 13% used for human consumption, 56% used as animal feed, and 20% for non-food uses such as bio-oil and ethanol. Rising demand for this crop is projected to reach around 1,218 million metric tons in 2024 globally and will increase in the coming years. With this, one strategy to meet these demands is to ensure high corn yields and productivity. This starts with ensuring that the seeds are of high quality with high germinability percentage. Seed germination indicates viability and potential plant performance, meaning a high germination rate produces maximum yield. Standard and conventional germination tests are still being utilized, which take around 7 to 14 days, requiring constant monitoring and a controlled environment. This method is labor intensive and time consuming. However, modern non-invasive, fast, and accurate techniques have been developed to obtain not just the germination rate, but also detect possible diseases and abnormalities, such as those optical-based evaluations, near-infrared spectroscopy, Fourier transform near-infrared, and hyperspectral imaging. Thermal imaging and spectroscopy-based assessment, such as Raman spectroscopy and electrical impedance spectroscopy, are also being utilized. So with the conventional method of conducting germination tests, which is labor-intensive and time-consuming, and while modern developed techniques even have proven to be effective, fast, and accurate, but they often require specialized equipment and operational expertise, which are really costly. There is a need for a rapid, non-invasive, precise, and cost-effective viability testing method that is easy to operate. With proven applications of electrical impedance spectroscopy on various seeds, there is a significant gap in using this technology to evaluate corn seed. Therefore, this study aimed to fill this gap by developing a rapid and non-invasive approach to classify viable and non-viable corn seeds using EIS with advanced machine learning models. Comparison based on different metrics between the 6 machine learning algorithms was performed to identify the most appropriate model for this classification. Furthermore, this study contributes to the green manufacturing by reducing corn seed viability testing time from 7 to 14 days to approximately 1 day, enhancing efficiency while aligning with sustainable practices. Employing a non-invasive rapid assessment method conserves resources, lowers cost, and accelerates seed distribution, thereby supporting optimal land use and improved corn production. This significant supports and aligns with the UN's Sustainable Development Goals or SDG numbers 2, Zero Hunger, 9, Industry, Innovation and Infrastructure, and 15, Life on Land. The methodology has two phases: data collection and machine learning modeling. For data collection, 50 viable and 50 non-viable seed samples were taken. An EIS evaluation board was utilized to extract the impedance spectra of each corn seed. From the extracted data, the impedance parameter was obtained and used in second phase. ML modeling was performed by cleaning and transforming the dataset based on the selected features. These features were fed to train and test various ML algorithms and determine the most appropriate model to classify viable and non-viable corn seeds. So for data collection, phase 1, corn seed sampling, the corn seed variety is the N6CN282, IES1004W, which belongs to the foundation class. These seeds were obtained from the Bureau of Plants Industry, Manila, Philippines. For the viable seeds, 50 seeds were chosen randomly from the acquired seeds from BPI. There's no further treatment done. For the non-viable seeds, 50 were chosen randomly and made non-viable through heat treatment by exposing them to 100 degrees Celsius for 30 minutes in a convection oven. Then, after preparing the samples, the collection of each seed spectra is performed, first setting up the experiment. The experimental setup is comprised of the EVAL AD5933EBZ evaluation board from Analog Devices Inc., 2.35 mm standard pin electrode ECG lead wire as probes, a corn seed holder which is made of non-conductive material, and a laptop. The evaluation board is paired with a dedicated software application that must be installed in a computer to perform frequency sweeps and extract the impedance data. Then, software configuration and calibration. Before initiating the frequency sweep, specific configurations must be set for this study. As you can see, these are the actual settings used in the study. The frequency range for the sweep is 400 kHz to 1 MHz, which is the optimal range in which viable and non-viable seeds can be distinguished. This can be achieved by setting the starting frequency to 400 kHz, delta frequency 10 kHz, increments of 60, settling time cycles is 15 MHz, the reference clock frequency is 16 MHz, output excitation is 2 volts peak to peak, PGA control gain is just times 1 as the multiplier. For the calibration impedance, resistor only R1 is chosen with a value of 0.1 ohms, which is the resistance of the electrodes used in this study. Default setting used are the DDS setting time cycles, which is times 1, calibration gain factor as midpoint frequency calibration, which will give the calculated gain factor used throughout the sweep. After the configuration and calibration, impedance spectra can be obtained by placing a single corn seed onto the holder to make contact with the probes. Then start the frequency sweep by clicking the Start Sweep button. The frequency sweep takes around 30 seconds. After approximately 30 seconds, the impedance spectra will be available to download in a .csv file by clicking the Download Impedance Data button. The downloaded impedance data contains the frequency and their corresponding measured impedance, phase, real part, imaginary part, and magnitude. The extraction of impedance parameters from the spectra is done by acquiring key features of each corn seed for this study. These are the maximum and minimum impedance with their corresponding frequency that will be used as predictor for the machine learning models. These features were chosen since they represent the extremities of impedance values, which are directly related to the seed electrical properties. The second phase is the machine learning modeling. Cleaning the dataset is an important part of this phase, as this removes the data that will not be used during training. Key features are extracted from each seed's impedance spectra and merged into a single Excel file. The data set was divided into 80% training set and a 20% test set using stratified sampling to ensure a balanced representation of viable and non-viable seeds in both subsets. Then, 6 optimized machine learning algorithms, including shallow and deep network models, were trained and evaluated. This includes regression tree, Gaussian process regression, support vector machine, and feed-forward neural network for the shallow network models. Spiking neural network and deep recurring neural network are for deep network models. Each algorithm utilizes one-hot encoding which characterizes the output into 1 and 0, demonstrating viable and non-viable classifications respectively. Unlike the conventional way of classification problem, this study used tandem of regression model with rounding off algorithm, to enhance classification performance and as a package to make a classifier model. Then, in order to identify the most appropriate model for classifying viable and non-viable corn seeds, each optimized machine learning algorithm is evaluated based on their accuracy, specificity, precision, sensitivity, F1 score, and Matthews correlation coefficient or MCC. So the results. For the results, the impedance value of each viable and non-viable seeds from 400 kilohertz to 1 megahertz is plotted and analyzed. The bioelectric impedance of the 50 viable corn seeds extracted from the evaluation board shows a distinct upward trend, with 134 point or 136.134 ohms as the maximum mean impedance at 990 kilohertz and 5.004 ohms as the minimum mean impedance at 440 kilohertz. Furthermore, the slope of the trend computed is 0.000164 ohms per hertz, peaking at 990 kilohertz. The overall mean impedance for the viable seeds is 57.042 ohms. On the other hand, the bioelectric impedance of the 50 non-viable corn seeds extracted from the evaluation board shows a distinct upward trend too, with 134.845 ohms as the maximum mean impedance peaking at 990 kilohertz and 6.337 ohms as the minimum mean impedance at 1 megahertz. Furthermore, the slope of the trend computed is 0.000127 ohms per hertz, peaking at 990 kilohertz. The overall mean impedance, sorry, the overall mean impedance for the viable seeds is 61.541 ohms. Moreover, it can be observed that the overall mean impedance of non-viable seeds is slightly higher than that of viable seeds, which could be because the non-viable seeds are drier than the viable seeds. This could be seen too in their physical appearances. The non-viable corn seeds have whiter and more solid-looking and drier appearance than the viable seeds in their endosperm part, as also observed in their front, back, and top parts. Furthermore, the machine learning models were trained and tested using MATLAB. The confusion matrix of each algorithm is generated. Finally, the R3 plus RO or the regression tree with rounding off model outperformed all other algorithms across every metric measured with 95% accuracy, 100% sensitivity, 90.90% specificity, 90% precision, 94.74% F1 score, and 90.45% MCC, and makes it most appropriate model for classifying viable and non-viable corn seeds. Its training and testing accuracies are at least 20% better than the deep network models. Here is a comparison of developed techniques and models versus the existing related works. Previous research in corn seeds viability classification uses optical-based approaches, and EIS approach is not utilized in corn seed viability tests, leaving a gap in corn seed viability studies. Furthermore, the accuracy of the developed model using EIS approach is comparable with that of previous studies that use optical-based approaches. Then, yun. Overall, the key takeaways for this study are: this is the first successful integration of electrical impedance spectroscopy with machine learning for the rapid and non-invasive classification of corn seed viability. EIS is found to be cost-effective and simpler to use than image-based method with comparable accuracy. Impedance data reveal distinct trends between viable and non-viable seeds with distinguishable impedance metrics. The R3 plus RO model outperformed all other algorithms across every metric measured with 95% accuracy, which makes it the most appropriate model for classifying viable and non-viable corn seeds. The developed model was successfully implemented, reducing the time of corn seed viability testing from 7 to 14 days to just 1 day, which leads to to cost savings and reduced resource use, aligning with green production goals and UN SDGs. So that's it. Thank you so much for your attention.